it's this many samples to the x minus 1 or whatever x is the number of samples minus 1 or something. Do you know what I'm talking about, or am I just babbling in a language that's foreign?
Yeah,
I know. I'm going to do a couple samples and see if I can figure out what I'm going to do if there's 5 plus 3, 1 plus 4. Whenever there's the sum of like the variances and whatever, and I'm like, there's an easier way to write this. It's the sum of the 1, 2, 3, 4, 5. Okay, then you got plus 3, 2 plus 4, 2 plus 5. Oh, I know what it is, but it's not. Yeah, it's one of those calculus. 1, 2, 3, 4, 5, and then that.
Is there a formula inside the lesson? Because the lesson was about ANOVA, right?
No, there's no formula.
Oh.
And I hate it when they do that. There's no formula that they provide us with. But I think it's something like that one that you do in calculus where it's the sum of the data raised to the n minus 1. So every time you go, it's, you know what I'm talking about? You're taking calculus.
I've taken it, but I don't know. I'm confused.
Okay, that's okay. It's okay. There is a formula that I think is simpler than what just writing it all out and figuring it out every time. So,
are you saying that we should do that you're talking about if you were to do the test, like comparing two groups and do instead of doing an ANOVA test?
Yes, because they refer to that and they say, well, okay, the chance of type 2 error is going to increase the more tests you do. So it's ideal to do an ANOVA test because then you're comparing them all at the same time and it reduces your degree of error. But they do not, and they say, yeah, so if there's 3 pairs, it's 1 plus 2, 1 plus 3, and 2 plus 3. So there's three samples, right? There's 3 comparisons going on within the software. And that's why we do it in the software and we don't do it by hand, for example. But if there's more samples, then it increases the number of samples that it's analyzing for us. And one of the questions in our quiz is, if there's more samples, how many pairs are we evaluating here? And I know that there's an equation that has not been given to us, but I'm going to see if I can figure it out based upon calculating out the first couple of examples and see if I can.
Man, you were...
I'm sorry.
You're far ahead of me.
Maybe I'm just not trying that hard and I'm just kind of taking it at face value and not thinking about it too much.
See, when it's something like that, I always try to think of, okay, is there a formula I can plug it into? And you know, so I always make up my own formulas when they don't give us one. That's what I always do, because I'm like, okay, this 3 sentences for describing what this is not working for me. I'm going to write out a formula so that I have something that's more concise in my brain. English is more fallible.
There's definitely got to be something that'll do it a little bit easier than...
And I know that there is, but I'm just not recalling what it is. So we've got 2 plus 3, so I'm going to do 3 plus 4. I'm writing out the 4 and the 5s so that I can see what I find is similar there. And then the 4 plus 5. No, 3 plus 5.
No.
And you see the pattern when you write them out is that you have one less test for every one you go up because you've already done the 1 plus 2. So you don't do the 2 plus 1 after that because you've done that comparison. So it's like an n minus 1 with n being the number of tests. And then it's the sum of all of that data. And there's a concise way to write that in calculus. It's like that weird E thing, which is the sum of whatever. And then you've got the limits on the bottom and the top of whatever the x plus 1 is to the n minus 1. And then it's 1 less every time. And maybe that does not help anyone but me, but it probably only helps me because I know that you guys do better with English than I do. 2, 3, 4, and 5, then 4 and 5, and then that one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if there was 5, it would be 10. 1, 2, 3, 4, 5, 6. And it's 6 if there's 4. I asked my husband. He would know like in 10 seconds. Or my son probably would too. But oh well. Okay. Sorry. I figured while we waited for people, but if everyone's here, I'm sorry that I'm holding people up. If everyone's here. Sorry.
No worries.
Sorry, I
My
wasn't
wife
looking.
like trying to ask me questions too. So.
I'm not even prepared, so.
Okay. So everybody have it open. There's 2 data sets this week, so make
Yep,
sure
I
you
got it.
open those real quick.
Let me open those.
I know Tim's on the school computer, so we won't be able to hear or see him. But if you have your chat open, he said he'd throw stuff in there if he needs to.
I don't normally go back and forth. Got the BM open on the other side. I thought that soccer shoe thing was kind of funny. Okay, we already did that one, kind of, sort of. Okay, open up soccer shoes. Okay, so let's start at the beginning while I'm opening that. 1 and 2 are typical. Oops, I don't want you. Move out of the way. Oh, always is right on top of my quiz. Okay, here we go. Man, my arms are shaking. Okay.
Okay,
I'm
so
supposed to be lifting my 3-year-old, and I had to carry him to the bus stop because my 6-year-old was ahead of him, and that's not acceptable. So I had to carry him all the way back and forth because he would not move his feet. Okay, so question 3. In a ANOVA hypothesis test, we reject a whole when there's sufficient evidence to indicate at least one mean is different from the others. True.
True.
Okay, I like that question. That's easy.
The data is normally distributed as one of them.
Yep, so number 2 and number 3.
So, ooh, where did my thing go? Variances are equal and normally distributed.
Yes, so 2 and 3 both on question 4. Those are the 2 main rules, or whatever you call those, requirements. Question 5. Please holler if people disagree.
I'm
I'm
checking. I haven't even looked at it, so.
Okay, so to check if each group is normally distributed, do the following. Construct the
QQ.
QQ plot for each group. Yep. Feels like there's a lot more of those things in this round than the other times. Question 6. We assume the variance is the same if the largest variance is less than 4 times the smallest variance. That's number 2.
Yep.
Which is weird, but that's what it is.
Yeah, I didn't read much into why they decided that, but
I always question. It helps my understanding when I question things, so it's more intuitive. Okay, this is the one I was talking about, the idea behind this. So if there's 3 samples, you have 1 and 2, 1 and 3, and 2 and 3, so that's 3. How many pairs when there's 4 samples? So you'd have 1 plus 2, 1 plus 3, 1 plus 4. Then you'd have 2 plus 3 and 2 plus 4, and then 3 plus 4. So that's 6, right?
oh, do you mean like a factorial? Is that what you're thinking about? Like 4 exclamation mark? Or like 1
Maybe.
times 2 times 3 times 4?
Something like, yeah, something similar to that. So
I don't.
you're getting my gist now. Yeah, that's the idea. That's what I'm
Yeah,
not sure
I'm
with
starting
the
to. I'm pretty
accurate
sure it's a
way.
factorial.
Okay.
So 4.
Okay.
Where's the button? It'd be 24. Is that not right? That sounds way high. Maybe I'm wrong
No.
then.
Well, but it's that idea. Yeah. So it's like the sum of the. So it's okay. So we have 1 plus 2 and 1 plus 3, 1 plus 4, and then we have 2 plus 3, 2 plus 4, and 3 plus 4. That's 6. Am I missing any of those? I think it's 6.
1 2 1 3 1 4 2 3
2 4
2 4
and then 3 4.
3 4. Yeah, 6. Unless they don't pair with themselves. I guess the factorial would be if they paired with themselves.
Would be paired with themselves. Yeah.
Yeah. And it's probably.
There's where the n-1 comes in, right there.
Yeah. Now I understand what you're talking about. I was just super confused because I was not on the same page, I guess.
Well, and I did the 10 one too, or this 5. The 5 would be 10. So I'm trying to figure out, okay, if it's 3 and 6 and 10, it's something like that. It's like 2 to the 3rd, so it's n-1, right? Because and with the 3, it would be the 1, and then the 3 minus 1 would be 2. No, but that's wrong. Okay, so maybe not. We'll figure that out. We don't need to figure it out. We're probably just, he's probably
Hopefully
not going to
they'll
ask
keep
us
the
like a
sets
large number.
small enough. Yeah.
Yeah, I would hope so. Okay, so what's the minimum smallest variance? Oh, I have to download. Okay, footwear, it looks like we need to transform the data. I still think every time of like Pokemon when I hear the transform. Okay, we want footwear to be coded. So let's do that. Footwear. My kids always want to show me. Look, it's transforming. My Pokemon is transforming. Okay, so transform the data. Okay, what do we want to do? We want the variances. So analyze. Seems like there's a lot more steps this time. Step the variance. We want descriptive. Explore. We want dependence. Kicking accuracy. Is that footwear?
Oh, my wife was showing me too that if you go into where was it? Options, you can make it do descriptives as well, so you only have to run it once. You don't have to like run it twice.
Oh, really?
Yeah, which I thought was kind of cool.
Okay, wait. We're not doing plots right now. Okay, so that's the one that I'll do later. So it's not the explore, then that's the good one. It's the other one that's the good one, right? The analyze, the compare means one way ANOVA. But does that doesn't give us the variances on all of them though, does it?
It gives
that's what we're looking for.
Some of the squares, DF, mean, square, F, and sig. But you can set it to do descriptives. So if you go in there and you're setting it up and then you press options, then there's a box you can check for descriptives.
Which I do every time. But the thing is, it doesn't show you the variances. So you've got the standard deviation, so you can do the work yourself and square them all. But I'm saying when you do the other one, it actually has the variances in their own little individual graphs. So you don't have to do the math if you don't want to.
What's the?
What are we looking for again? The minimum.
Yeah, the smallest variance for the 4 groups.
We've got a 31. We've got a 53. We've got a 27 and a 29 and a 27. So go back down. 27. Now wait, one was 27.2. 27. That's so. Is C the smallest one? Oops, I passed it. That's a 40. 31. I think it's the third one. Is the smallest one. The C. Do you agree that that's the smallest variance? Smallest variance, 27.208. That's the smallest one I see. I can write them all down though. I probably ought to. Let me do that.
I guess I'm just confused what you did.
Are you looking at the descriptive?
53.158. Well, when you do the analyze, if you do the descriptive statistics exploring, go do all of that right, then it gives you the list of each individual one with all their different things in it. And then then that, because it has the variances in there as well. Or you can square all the standard deviations yourself. That's what I was saying, is that if you want to not do that, then you do the other, because your wife is right, but we were doing that anyway with the ANOVA stuff and already putting that in. So that has all the other information we need.
All you're really looking at is which one has the lowest standard deviation and then squaring that. And so it would be C.
But yes, I guess you could do that.
So 27.206, which is...
But the variance that's listed, if you do it the other way, is 27.208.
Yeah, they must have just kept more figures there.
Yeah. And so, let me write those all down.
Yeah, it's kind of hard, but which one do you... Well, I mean, probably you should take the one that's more accurate.
So probably the one in the descriptive
208
Explorer then, right?
Yeah, 27.208.
Okay, so 8B is 29.4.
Okay.
C we already have. D is 53.158, and that was the largest.
D is going to have the
You're
largest.
asking us that next. Yeah, D has the largest. It's 53.158. And then the socks, no, not the socks. E, there's a socks as well. Okay. I would not like to go kick soccer balls with your socks only. That would not feel good, especially if the field's like slick or anything. Yeah, why is that?
The test for equal variance is satisfied. So then you got to do.
Go back up. Come on. There we go. Socks. 4724. Is that what they're asking us in 9? No. Is that in 10? Okay, I was still trying to get through all that data. Smallest was 27.208. 9 maximum was the 53.158. Oops. Oops. Except, was it? Yeah. Okay. 10. The test is satisfied. You said true. Did we do that on the homework? Is that on our preparation? Did we do the socks and the stuff?
Okay, so the test for equal variance is satisfied for these data because you do the QQ and it looks normal, right? Is everyone? Is that what you're seeing? Which one are you on, Tawny? Just I feel like
I was writing everything down as usual, so I don't have to go back and find it again in my thing. So this is number 8. This is number 9. Hold on. So the largest, yes. Okay, so 10 is true. 11. We do the QQ plots real quick. Oops, I'm doing the wrong thing. Nope. Destructive statistics. QQ accuracy. I think I'm doing this wrong. I'm going in about it the wrong way. Let me go back.
Can you show me your QQ plot? I just want to see how much mine is.
The plots, that's where I want to get that. Okay, normality plots with tests. There we go. There we go. I don't know what the point of that one plot is.
is this what we're going for here?
Yeah, that's what I know. Okay.
Okay, next it wants a QQ. So that one, you'd say it's true that the variance, there's equal variance because it follows the, I mean, it's right along the line, right?
Right.
Okay, and so then now it wants us to make a QQ plot for each of the 6 samples. I guess I'm confused how to easily.
How do we do that?
You do that with your other thing, that's descriptive statistics. Okay. Explore. Make sure your things are in there, and when you go into Explore, I'm not going to do it again because I just did it. And you make sure your dependent list is in there, the kicking accuracy, the factor list is the footwork code, and go into plots. And click on the normality plots with tests. And that's how it comes up with the 5.
Okay, that's why I was confused. Oh, it's so much to look at now.
I know, seriously, that's why I keep going through all this stuff.
So I click on normality plots with tests?
Click on normality plots,
Okay.
So
and that's going to pull all the QQs up. And you don't want the detrended ones that are at the bottom. You want the ones that are at the top.
That are angled.
Which is called normal QQ plots.
B's the only one that's kind of like, ugh. But I mean, if you're looking at it like,
is they always make you look at it and then they say, well, it doesn't matter if it's right or not. Just go ahead. Like,
I think
we're just going to assume that it is. That's always what they do.
I think the thing to look for, because B's the one that's a little strange, is we want it to follow the trend. So yeah, they're following the trend, and about half of them are above and half of them are below. Still be normal, even though it's a little ugly. And then the rest of them are, I mean, pretty darn normal looking. Okay, so for 10, are we saying true, and 11 we're saying true?
Yes.
Okay.
I think so. They look approximately normal.
Of course, now my computer doesn't think I have a camera because I stopped using it.
Let's see. Let's go back up to the ANOVA test.
Yeah,
That's the thing. There's so much data here that it's just like, oh. Let me go back and find what I'm looking for here. Or I could just run it again, which is, there we go. ANOVA test. Here we are. Observe the p-value is 0.081. Good. Yes, it is.
I just have to find mine again.
Yes, or true. Was our 12. I know it's like serious, right?
Okay. Oh, yeah. Stig is 0.81, the p-value.
Remove the sock data. Okay, we got to do some stuff. They haven't had us do that before, so we can do it though. Okay, so let's go find the socks. Great. Come on. So we want to take out socks, which was just...
That should be 6, right?
6, yeah. So are we just going to erase the data for all of that? For the whole column?
That's what I'm trying to look. Is there a way to do that without?
We don't have to save it. Yeah, just highlight all of that data and delete. And then let's try again. Analyze. What do they want us to do though? I don't want to do the difficult way. We're just doing the ANOVA test. Okay, let's do that.
Man, there's got to be an easier way than deleting the data and...
That's what he said. Somebody asked a question about that on the discussion board, and he said, just go out and take it out. But it wasn't on this particular thing.
That just sounds annoying.
Yeah. Well, at least we know we're not screwing it up that
we
way.
can just remove footwear code. I guess it's 6.
We could, but in this one, it doesn't ask us for the numbers. So that might be more difficult. I just took it out. I'm just doing it that way. Okay, so with only those A through E, the level of significance without socks is 0.309.
Yep, that's what I got.
Okay, so is that what they want to know?
What is the p-value when we remove the socks?
0.309. The socks should not be pertinent unless that's a control group anyway, right?
Is the p-value the area to the right or left?
It's to the right.
Okay, how do you know that? Sorry.
Because it's always to the right.
It's always to the right.
It's a right skewed, and it's that part that approaches 0 after the distribution.
Who's asking? Oh, because it's positive, it's to the right. Yeah.
Well, it's always to the right.
Positive,
that's the only way it ever works with this kind of test.
Okay, get rid of this
Hot
soccer
dog nutrition. Hot dog nutrition. Fabulous. QQ plots for the calories. Okay. Well, let's open this.
So it wants an individual one for each of them?
Yeah, that's what we did last time too, though.
Okay, transform, automatic recode.
Hot dogs. Ooh, come on. You know what else transform makes me think of? Have you ever played or seen that game, the Mario Galaxy, Super Mario Galaxy, where the stars transform?
Yeah.
Oh, yeah.
That's another thing that comes to my mind every time. That's what I'm thinking of more than the Pokemon. Okay, so we're just doing the calories. No, we're doing type. Sorry, I'm doing the wrong thing here. Type of hot dog we want to code. Code. Add new name. Okay. I'm going to get rid of the soccer shoes because there's too many things here.
And it wants us to make a QQ for just the calories, but one for each of the different types.
Right. It does that automatically if you do it through the way I said. I don't know about the other direction because I haven't.
Mine's just having
So if you do
error codes.
Descriptive statistics, calories in the dependent list, type code in the factor list, and go to plots and click normality plots. Actually, I'm taking out the stem and leaf because we never use that and it always wants to do that. Then it should come up with what we want. All of them separate.
Did yours have a bunch of errors?
Nope.
Okay, so your dependent list was whatever your coded thing was, right? Oh no, never mind. I think I did mine backwards. Yeah, I did mine. No wonder I have all the issues.
So let's see. Normal QQ plots of calories. Okay. Yeah, and kind of, and yeah, they look kind of. Yeah. So there's only 3 types. Woohoo!
That one looks pretty normal. These are definitely a lot more ugly, but.
Hey, let's see what it says. Safe to assume each comes from that. Actually, I want to look at the number of samples too, because that's good. It looks like there's like a good dozen or so for each, right? See, it doesn't tell us in this one. Go up. There we go. 20 and 17 and 17. Okay, well, so it doesn't do it because of that rule. The assumptions have, all of them say have not been met except for the top one.
Yeah, I'm thinking it's not met because those are really ugly QQs.
It's not safe to assume it. So the bottom one?
We cannot assume they are equal.
So they're not all normally distributed.
It has to be the bottom one if it's not been met, though, right? It's not safe to assume that.
Well, there's one that says it's safe to assume they're normally distributed, but the variants are not equal.
Which one is it?
The second one.
I don't know when we decide that.
Can we see if the data is normally distributed?
Make a histogram. Let me do a histogram and see what we got here. Calories, type code. Are you guys the ones texting? Rows, type code. Let's take a look at these. Oh, 13 was right. Did you get that, Tim? He just asked if it was left or right. It's right.
Oh.
Okay, histograms. Let's look at these. Well, the meat one is not normally distributed, for sure. Yeah, they don't really look normally distributed.
Okay, so what we have to do, it's, so the answer is either the second to last one or the last one. So now we just need to assume whether or not the variances are equal.
Variances are equal.
So
okay, that's fair. So
when you're looking at those QQ plots, is it just the QQ plots have to look the same as each other, or is it?
I thought they just had to be along the line. And in the other test, I think that they would say, well, it's normal enough. We're going to assume that it's approximately normal.
But how do
That's what it feels like. They've always done that. Oh, the variances, we have to do that. Analyzing stuff to find that. Analyze descriptive statistics, explore. Calories type code, you're going to go under options. No, wrong one. You're going to go under, no, I'm in the wrong one. Sorry, hang on, let me exit out of it. It's not that one. It's the analyze. It should be under that. Huh. It should be under that. Let me see. Oh, under statistics.
So wait, you're saying that it's not normally distributed for the calories?
Honestly, I don't know even what to tell you there, because I think it looks like it's so similar to all the other ones I think we look at that they always say, yeah, that's approximately normal. That
It looks, I don't, Here, can you look at mine and tell me if I did that? I have the
Yeah.
same one as you because, one second, let me make it big enough you can see it. Is that what yours looks like?
No. I have 3.
Oh, you did them all individually. Oh, maybe that's why.
Well,
Oh, yeah.
together.
Well, together they are, but it's the individual ones we need to look at. Yeah. I see what's going on here. So one of them wasn't, and so that disqualifies all of it.
Yeah, I think so.
Okay, that makes sense. That's where I was confused. That makes sense.
This isn't the one I'm looking for. Type code, options, descriptive, range plot. Okay. So we've got 2017 and 17.
How'd you do those individually? You just did histogram with the variable as calories and then the rows as, or no, that wouldn't change it.
Yes, I did, actually.
You just threw the...
I did the histogram, and then I did the calories as the variable and the rows as type code. And just them 3 right on top of each other in one picture.
Oh, that's why.
Okay, hang on a second. Let me
Very
see if I can
cool.
find.
So you're saying meat is the one that wasn't normal?
Yes. Yeah.
Yeah,
That's what I think, right?
I can definitely agree with that.
Okay.
Okay,
So,
that's super cool. Thanks.
So
how do you determine? How do you assume the variances are equal?
well, we do the variance test where we compare the variances, and if the largest variance is less than 4 times the smallest, then we assume that they're, what wording did they use? Then we assume that they appear to be similar. I always have to look up how they say it because I'm just like, I'm trying to.
So we make the QQ plots, and then are we getting the variance off the QQ plots? I guess if we're just going to look at the distribution times 4, what's the point behind the QQ plot?
They want us to evaluate all of that first.
So look at the QQ plot, say, oh, it's kind of hard to tell. Let's analyze the data and do an actual calculation.
Whenever they give us questions, they always say, regardless of what you come up with, go ahead and do the problem the way that you would if it was. That's what they always do to us. One of them, that was our homework or something, that I didn't think it was normal. Let's see which one it was, or maybe it was in our homework, and it wasn't, or something.
So one of them has to be more than 4 times of another one.
The largest
has to be less than 4 times the smallest. So if we look at these, the smallest standard deviation, 22.642. Oops, let me turn on the calculator. Would be our smallest. When you square that, then we were going to have 512.60. So 4 times that, and then what's the largest one here? Largest one is the 29.383.
Yeah, that's less than four times by a large margin. So then the answer would be that we can assume the variances are equal, but we can't assume they're normally distributed.
Yeah, so the third one?
Yeah.
Okay, I agree with that.
We're running a Nova now. 251.
Oh, come on. Question 14, we're saying the third. All right. So not normal, but variances equal. Okay. Determine the mean number of calories is the same for all 3 types. Degrees of freedom are 2 and 51. Okay, I agree with that. F is 16.074, I agree, and P is yes. So what conclusion can we draw? We don't even have to run anything to do that because they give us all the numbers.
Yeah.
Right? So the P is less than the level of significance. So we reject the host. So we say we have sufficient evidence to claim that they have a different mean calories. Right? Because our alternative hypothesis is always that
one of them is the one of the means is different. So since we rejected the null is that they all have the same. So if we're rejecting the null,
we want the third one, right? We have sufficient evidence to claim that all three have a different mean.
Yep.
Or let me see. Or wait. No, sorry. The bottom one we want. We have sufficient evidence to claim that at least one of the hot dog types has a different mean.
Way to read all of them, Tawny. Yeah.
I've learned to do that in psychology because there's always a trick.
Oh gosh, yeah. That's just not nice of them.
Oh no, it's not. Oh, it makes me crazy. We have sufficient evidence to claim that at least one is different. Okay. 16.
So
we all agree. I haven't seen anything from Tim for a while, so I think he must agree with us.
Histogram, but this time we're doing sodium.
All right.
They all look normally distributed with the histogram.
Analyze, compare means, note descriptive, explore. Let's put in our different things. Calories, you're out. Sodium, you're in. Plots. Excellent. We're doing QQs. Okay, let's see what we got. This is for sodium. Excellent. I always make this so big I can't fit it in my screen. There we go. Scoot over. Okay, let's take a look at these plots. What we got here? It looked like the other ones did. Like the bottom one, the poultry has more sodium difference distributed, right? You should see the poultry. Aha! I was right. The smallest variance is blah blah blah. 7180.75, and the largest is 10,492.7. Yeah, that's gonna. So we know that we can assume the variances are approximately equal based upon those numbers they give us.
Mm-hmm.
But the QQ plots look fishy again.
It's so fishy.
So which one do we want? The assumptions have not been met. It is not safe. Okay. So 3? 3, yes? It looks fishy in the QQs, so it's not safe to assume the normal distribution, but we can assume the variances are equal because the 10,000 whatever is less than or equal to 4 times the 7,000. Yeah?
Wait. Don't they have to have an equally distributed variance to meet the assumptions?
Yeah. But
and
we're saying
so the smallest is within that range of the largest, so they do meet the assumptions.
Right. The variance, we can assume the variances are equal. That's why I'm saying number 3, because it says that the normal distribution is in question, but the variances are fine. Isn't that how you read that? That's how I read that.
Oh, okay. Yeah. But isn't it normally distributed? I did a distribution and it looked pretty normally distributed to me.
Well, the poultry looks fishy. It looks like the other one that they said they didn't like. And they tell us at the beginning, it says you should see that the poultry one suggests a possible problem. Okay. So.
Yeah, I see that now.
So do you agree that that's probably what they're searching for?
Yeah, that's definitely the answer. But I don't know. Okay. That'd be so hard to decide if I were taking a test or something. Because
yeah, I agree.
Not horribly off, but
only because they say so up there.
Right. Yeah. That's the reason. But I did look at the QQ plots first. See, despite the problem, you decide to use this. Exactly. That's what they always do to us. They do that every time. So.
Yeah.
So if I had to assume on my own, I would probably be wrong.
Yeah.
I know, me too, with all those, because it always makes us do that. Okay, let's do the ANOVA test here. One-way ANOVA. We got sodium. Take out the calories. Put
Sig.
in the sodium.
179, or I mean 0.179.
1 second.
Yeah.
Sweet.
0.179. Yep. 17.
So we do not
P-value.
have sufficient evidence.
0.179. Well, what was our level of confidence or interval? What is that called? What's our alpha? 0.05?
Level of significance.
Yeah, that's what it is. Too many words for me. I'm telling you, give me symbols or give me death. 179. Boy. Seriously.
So we're gonna.
It's right there. It's in the next question. Thank you. I did not even go down yet. 0.05. So it's greater than that. So we do not.
We fail to
reject
reject.
it. Right. So 18p is greater than alpha. So we do not have sufficient evidence to reject the claim. Is that what you come to as well?
Yeah, that's what I got.
So we do not have sufficient to reject that they all have the same medium sodium levels.
The second one then, right?
Yeah.
It's the only option. We could read them all though and just make sure they didn't throw in a one word changer, game changer.
For question 14, we got the assumption has not been met, and that it is not the third one.
Third one, it's
yep,
not
the third
normally
one,
distributed, but the variances are approximately equal.
I gotcha. Yeah, okay.
Submit.
I hope that's.
Do it.
What?
95. We missed one of them.
Which one?
14.
Oh.
14. It's words one, right? Yes, it's words. Okay. We do fine with our numbers. It's the words that I have trouble with. Okay. So we said the assumptions have not been met. It's not safe to assume. Okay, which one is this on the calories?
Yeah, calories of the 3 hot dogs.
For each of them, they recorded those things. Okay. So the variances were equal, I think. So are we going to say that the next best option is it that the QQ plots were normal, and so we can say the assumptions have been met?
Yeah, I think it's A,
That's
or
the
first one.
That's the most likely next one, right?
Right. I think that's
because the variances were fine.
Yeah, somebody give it a shot and see what happens.
Okay, I will give it a shot. Let's see what we got here. Yep, that's it.
Cool.
That's the one we want. So that was 14, and it was the first one then. Okay.
Woo.
Well, the next one's the long one. So got to go do our
So
test
the prep is the exact same questions, right? So if we all do the prep, we should be able to walk into it and just go through our answers and discuss anything we think is different.
Yes.
Okay.
I don't think it should take.
Last time I didn't put, a ton of effort into the prep because I was like, why take a huge long quiz completely with all my effort if I'm just going to go walk into a completely different quiz? But if it's going to be the exact same quiz, then
I think it's going to be pretty close. It implied that it was pretty
seemed
close,
like,
and there may be some things on there that might not be on the quiz, but or maybe that weren't going to be on the test. Stupid squirrel, get out of my, oh, it's stealing my apples. Stupid squirrel.
So we're saying the assumptions have been met for 14 then, just so I can.
So the first one, the assumptions have been met.
I'm just trying to redo my answers real quick.
Yeah. The assumptions have been met. It's safe to assume it's normally distributed. Those are the ones that are going to kill us because there's too many words. At least for my liking. I need to take more math clearly and less psychology. Not really.
There we go, 100%.
Yep, that one's good.
Deal.
So yeah, go through and do all of the test prep stuff, and we can discuss anything, because I think that helps my understanding when we talk about the stuff.
Yeah.
When there's words, I just want to talk about it and make sure that I'm in the same place that everyone else is.
Okay, I'll post it online, and I'll remember to include Tim this time.
Okay.
I felt so bad about that.
He cut you out, Tim.
Yeah, that's so awkward.
Like, he was late, but I think he still gets credit.
I just thought I had everybody's name. I wasn't even thinking about it.
Yeah.
Here, I'll put him right here.
Put him first this time.
Awesome. I'm down twice.
Get double credit. Maybe that would work. We should try that. We should try it.
All right. We'll see you next week.
Okay.
Thank you, guys.
Next week. I'll post it up.
Yeah.
Okay, bye.
Bye, everybody.